Basking in the glory of a successful moon landing, India's space agency ISRO is all set for a further leap into the cosmos. This time, India is eyeing the Sun. On the 2nd of September, PSLV C57 rocket will blaze into the skies carrying Aditya L1. India's Sun mission will reach its operational position after an over 120-day voyage. It will get there by performing a complex series of orbits around the Earth, so-called slingshot gravity assist maneuvers that help save propellant. The same technique used for ISRO's Moon and Mars missions. The spacecraft is planned to be placed in a halo orbit around Lagrangian point 1 of the Sun-Earth system, which is about 1.5 kilometers from the Earth, where it will remain for about 5 years observing our star. But why spend so much time and energy going close to the Sun? The spacecraft will be carrying 7 payloads to observe the Sun's outermost layers. From time to time, the Sun is shaken by violent eruptions. Hot jets of plasma shoot from the surface as the Sun's intense inner motion disturbs its magnetic field lines. Waves are sent through the atmosphere hundreds of thousands of kilometers high and at temperatures rising to 100 million degrees. While NASA and the European Space Agency have previously placed orbiters to study the Sun, it will be the first such mission for India. Going by the distance and the experiments, Aditya L1 mission is a complex and challenging task, but it has the potential to provide valuable insights into the Sun and its impact on the Earth.
Aditya L1 is India's first solar mission, and in this video, we will explain why this mission is focused on the Sun and how the Aditya L1 will work. We know the Earth is the third planet from the Sun, and the Sun is the center of our solar system. The Aditya L1 will not land on the Sun. It will be positioned at the Sun-Earth L1 Lagrange point. To understand this mission, we need to delve into the layers of the Sun. This is core, the hottest part of the Sun, where the process of nuclear fusion occurs, converting hydrogen into helium. This fundamental process is what powers the Sun and provides the energy that sustains our solar system. The second layer is the radiative zone, where energy is carried in all directions by photon particles through a process called radiation. The third layer, known as the convective zone, is a turbulent, boiling plasma region that transfers energy outward through convection. This zone plays a crucial role in moving the intense heat from the Sun's core to its surface. This is photosphere. It has a thickness of about 500 kilometers, and all the visible light from the Sun comes from this layer. Here the temperature comes down to approximately 5,500 degrees Celsius, or 9,900 degrees Fahrenheit, which is much cooler than the Sun's core. The fifth layer is chromosphere, where the temperature begins to rise again. It is seen only during eclipses or with special solar viewing equipment. And the Sun's outer layer, called the corona, it is much hotter, about 200 times than its surface, the photosphere. Though the Sun does not have a solid surface like Earth. However, the fundamental principle says that temperature typically decreases as you move farther away from a heat source. But here the outermost layer is hotter than the surface layer. This unexpected temperature variation is known as the coronal heating problem. And the scientists have been trying to figure out why it happens for many years. The Aditya L1 will be placed in a halo orbit around the Lagrange point L1 of the Sun-Earth system, which is about 1.5 million kilometers from the Earth. Let's understand the halo orbit. If you see this graphic, there are 5 points around the Sun: L1, L2, L3, L4, and L5. ISRO set this mission for L1. That's why this mission is Aditya L1. Halo orbits are a special class of three-dimensional periodic orbits that result from the gravitational interaction between two celestial bodies, such as the Sun and a spacecraft. In the case of Sun-centered halo orbits, the gravitational forces from the Sun and the spacecraft's own propulsion system are balanced in such a way that the spacecraft effectively hovers in a region of space relative to the Sun. The major advantage of continuously viewing the Sun without any occultation, eclipses. This will provide a greater advantage in observing solar activities and their effect on space weather in real time. The Earth's ozone layer provides protection against various harmful solar radiations, including visible light, ultraviolet light, and infrared radiation, safeguarding life on our planet. It is good for our lives, but to study against such radiation, this mission becomes crucial for future studies. Aditya L1 will be positioned around 1.5 million kilometers from Earth, facing the Sun, which is roughly 1% of the Earth's sun distance. The journey to this location takes almost 125 days. Once there, it can transmit data for a period of 5 years. The 7 payloads on board Aditya L1 are Visible Emission Line Coronagraph, or VELC. This device will provide a wealth of solar images daily, contributing to the understanding of the Sun's corona and its behavior. Solar Ultraviolet Imaging Telescope, or SUIT. The SUITs will provide most crucial information to understand the problem of coronal heating, coronal mass ejection, pre-flare, and flare activities. Solar Low Energy X-ray Spectrometer, or SOLEXes. This payload is designed to measure the solar soft X-ray flux to study solar flares. High Energy L1 Orbiting X-ray Spectrometer, or HEL10S. This payload will measure the spectrum of the solar X-rays in the high energy range. Aditya Solar Wind Particle Experiment, or ASPEX. ASPEX-I consist of SWIS and STEPS. This payload will measure the properties of the energetic particles in the solar wind, such as their energy, charge, and mass. Plasma Analyzer Package for Aditya, or PAPA. It will measure the properties of the solar wind plasma, such as its density, temperature, and composition. It will help to study the interaction between the solar wind and the Earth's magnetosphere. And advanced triaxial high-resolution digital magnetometers. Magnetometer payload is capable of measuring interplanetary magnetic fields at the L1 point. Thank you for your patience and for